that happen with first order are normal. They're not normal. They're just specific for first order systems, but we know how to solve them, so you see lots of them. So it's a little bias of teaching. When you teach, you try to teach problems that you know how to solve. And not just teach, also people can research. Now, I'm being a little exaggerating a little bit there. The other reason why first order systems are very useful is when you're close to an equilibrium or a steady state. So if you're not too far from a steady state or an equilibrium, then usually you can represent things in a Taylor series about that steady state or equilibrium. And if they're not too far, you only need to keep the linear term. So in many cases, if you're close to a steady state or close to equilibrium, even if the real kinetics are not first order, as long as you're close, the Taylor series about the equilibrium or about the steady state will give you something that, as long as you stay close, looks first order. So it's not quite as bad as I said. There are many situations with first order where non-linear systems appear linear as long as you're close to the equilibrium or steady state. Okay, so any questions on that? And those are a little bit general concerns that are not really exactly pertinent to the class. They're more to put it in a context, in a more general context. Okay, so now I just discussed what happens if reactions are not first order. What happens if they're not irreversible? What happens if both of these reactions are reversible? Well, if they're reversible, then sort of all hell breaks loose. Why does all hell break loose? Remember I told you for the irreversible case, it was important to choose initial conditions so carefully so that the green curve had a maximum. If I chose my initial conditions here, 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 and here, then R wouldn't have a maximum anymore. Well, that's if it's irreversible. If they're reversible, then you can imagine things moving back and forth around here because we're not just going in one direction. So the safety of choosing my initial conditions here to get a maximum, because the reactions only go one way, is gone. Reactions go both ways. So depending on my initial conditions and depending on the rate constants, I may or may not get a maximum. In other words, everything's possible then. So it's hard to make general conclusions. What you need to do is, for a given set of initial conditions and a given set of rate constants, you need to make your curve to find A, R, and S as a function of tau. Because by changing the rate constants, the forward and reverse rate constants, and or changing the initial conditions, you can effectively, it's like changing the initial conditions somewhere here. So you can't make a general statement. You have to look specifically at the rate constants that you choose and the initial conditions that you choose. And I believe your book gives you a bunch of pictures for choosing different rate constants, and you see how the curves look very different. Okay, are there any questions on that? Well, we've spoken about series reactions and parallel reactions. And now I'd like to combine them into combined series parallel reactions. What do I mean by series parallel reactions? Well, let's look at, say, A plus B goes to R, and R plus B goes to S, etc. I could then do S plus B goes to T, etc. Now, first of all, let's think, when might we see such reactions? So let's imagine that I go S plus B goes to T, T plus B goes to U, etc. Can anyone look at these reactions and see if they remind them of some sort of type of reaction you may have come across in your academic life?
Radical reactions.
Identify what's what.
So A is non-free radical. B would be a radical, it would form another radical. R is another radical, and then that radical would attack, or no. A and B are non-radicals. They form a radical R. R starts attacking A and B.
Well, it's not attacking A, it's only attacking B.
Attacking B. It forms more radicals.
But then, so here you're saying you have a radical. Okay, what happened to A and B? A and B combined and gave me a radical?
Well, you have some, like some HB or some instigator that starts the reaction. And then R is a material radical to B.
What other kinds of reactions are there that this might fit?
Chain reaction?
Chain reaction? The chain reaction goes round and round. It doesn't give you have 10,000 reactions. Think of the fact that I can have a lot of these. So I have A plus B, and B is always there. Is it giving me an R? R plus B. Catalytic reaction, the catalyst doesn't change. So you'd see the same thing on both sides of the reaction.
You have a different enzyme in your enzyme.
But then the enzyme keeps coming back. I should have the enzyme on the other side of the equation. Well, how would that work? So the suggestion was polymerization. How would that work?
So A plus B combined to make a monomer, and then the monomer will react.
A plus B combined to give me a monomer?
Meaning,
Usually in polymerization, you have monomers to begin with.
right, so two monomers combined give you, it's like a single, so A and B are two monomers, they combine to give you another monomer.
Two monomers combined to give you a monomer? Dimer.
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 And then that dimer combines with one of the
Okay, so two monomers combine to give me a dimer. A dimer and a monomer give me a trimer. A trimer and a monomer give me a tetramer, etc. So this is a reasonable model for a polymerization reaction. Okay, so I'm just going to simplify it with just two steps, just because I want to keep the algebra manageable. But you can see sort of where we're going with this. Now I claim this is series parallel. Why is it series parallel? Well, let's look at it in, put B in the background. That is, we could write this as A goes to R in the presence of B, and R goes to S in the presence of B. So if I just look at A, R, and S, it kind of looks like a series reaction. On the other hand, I could also look at it as A goes, as B goes to R in the presence of A, and B goes to S in the presence of R. So with respect to A, it looks series, and with respect to B, it looks parallel. So it can go either way. And I think that's legal in certain states now after this. Okay, so let's see what happens. Forgot that. Okay, so let's see what we can do there. Yeah, so let's do an imaginary experiment. If we do an imaginary experiment, again, with as far as mixing goes. So let's look at a situation, two situations. Put them side by side. So in one case, I'm going to look at B, a big tub of B, where I'm putting in drops of A. And another one, I'm going to look at a big tub of A, where I put in little drops of B. And I'd like to figure out what's going on in these two tubs, to get a feel for the difference here. Okay, so what I'd like to do is I'd like to plot A, B, R, and S. Sorry, I'm stuck with blue. I don't have that many colors. Well, I have yellow. B, R, S. Okay, so first things, so what happens here is I'm going to use the same color scheme here. A, Okay, so what happens here? A drop of A comes in, and it gets reacted away. So for a long time, as long as I have a lot of B around, I don't see any A. I don't see any A. So A is sitting around at the bottom. B, on the other hand, as I put A in, I start chewing up B's. For every drop of A I put in, I get rid of a B. At least one B, and sometimes more than one B, because I form an R on that, then and that eats up more B. So the A's start going down. I'm sorry, the B's. A's are, the B's start going down. Now what happens to the R's? What was that? What happens to the R's? I put a drop of A in a ton of B. What happens to the R? I can't hear you. So what do I see for R? I don't see any R because I've got a ton of B. As soon as I form a little R, it has a ton of B and it goes to S. So I don't see any R for a while. And I start seeing S. I start seeing S immediately. As soon as I put a drop of A in, it goes all the way to S. So I start seeing S going up. At some point, there isn't a whole hell of a lot of B left. So B starts going down more slowly. And that's when I start seeing R come up. Because I don't have as much R anymore to kill it off. And I start seeing A come up, because A isn't getting reacted away right away. But by this point, I've got tons of S. So basically, in this case, when I have drops of A into B, I don't see much A and I don't see much R. Remember, in the end, we're interested in R, because typically, when you make a polymer, there's a certain size range you want. You don't want you usually want a fairly tight size range. So instead of having 2 reactions, you may have 1,000 reactions or 10,000 reactions, but usually you want to control the size of the polymer. You usually don't want some of them that are length 2, some of them that are length 1,000,000, some of them that are length 1,000. You usually want, say, between, let's make up a number, between 2,000 and 2,500, certain size range. So that's like going for an intermediate. If you let it go further, you get much bigger ones. Cut it off earlier, you get much smaller ones. Let's look at this. I put a drop of B in. Put a drop of B in, the B disappears, and I form R. I'm sorry, the B disappears immediately, and I form a little R. But there's no more B left for R to react with. So I put a little more B in. I form a little more R, because A is overwhelming R. And it isn't until I've put enough B in that I've decreased A that R starts going down. So A, I start out with lots of A, and A starts going down, and R starts going up. And it isn't until I have lots of R that the B can find R's before it finds A's. Then I start getting S's. And you can follow the logic and you get basically the same logic we had in the series reactions over there. And of course, once I've used up things, then I start seeing the B start increasing. Now, let's also do the linear algebra. So I've got A, B, R, and S. And I have my 2 reactions. So what's the reaction vector for the first reaction?
-1, -1, 0.
And for the second reaction? Good. Okay. So let's notice that as far as A, R, and S go, I have the same vectors I had before. Where did they go? Yeah. A, R, S, minus 1, 1, 0, minus 1, 1, 0. A, R, S, 0, minus 1, 1. 0, minus 1, 1. So one perpendicular vector is going to be, so the perpendicular vectors is going to be one that's 1, 1, 1 with a 0. I just saw that immediately from that. The other perpendicular vector, another perpendicular vector, is something that involves B. So I know I've got to have a B in there. So let's see what other vector I can have that's perpendicular. Well, let's see if I can form perpendicular vector just with B, R, and S. Let's see if there's an obvious one. Yeah. How about if I take this plus twice this? 0, 1, 1, 2. So if I do that, 0, 1, 1, 2, then minus 1 plus 1 plus 0 is 0. Minus 1 minus 2 plus 2 is 0. Now what's the logic behind that? Okay, that's just algebra. But that's telling me that for every S I form, I needed 2 B's. For every R I form, I needed 1 B. So this is sort of codifying that. For S needed 2 B's, R needed 1 B, and here are the B's. So every S required 2 B's, this B and this B, and every R only required 1 B. So that's sort of in words saying what that's saying. So what are my conservation conditions? This one says delta CA plus delta CR plus delta CS equals 0. And that's because it looks like series reactions with respect to A. And this says delta CB plus delta CR plus 2 delta CS equals 0. I'm listening.
So,
You don't have to say question 12 times, ask the question.
all right, so if it's not immediately obvious how you could break down these reactions into series and parallel, then you use the conservation conditions to generate those.
Yeah, I mean, this is just for instructional purposes that I'm breaking it down into series and parallel. I mean, usually you just handle it with the formulas. But for instructional purposes, I'm trying to break it. Sometimes if you can break it down, it gives you some intuition. But there's no guarantee that you can always break it down. In this case, we've devised it so that you can break it down. Now, since it looks like a series reaction with respect to A, if I'm interested in R, from what we've learned, we want to how would we want to introduce A? Plug method or series method, or CSTR method? Plug, because for plug, when I have reactions in series, then I do better for the intermediate. So at least from here, we see that we would like to introduce A in a plug fashion. Now it's not clear how I want to introduce R, whether I want it to be in a plug fashion or a distributed fashion. What do I want to say about that? So whether I want to introduce B this way or B this way, that is, have a high concentration of B or low concentration of B, is not clear yet. We have to do the analysis with the phi's to see that. So that's not clear yet. We need We need to determine that. But A, we definitely want to bring in plug flow fashion. Okay, so why don't we do the analysis, or as much of the analysis as we can do, but we can do algebra really quickly. So let's do the batch case, or the plug flow. Okay, so let's look at the plug flow case. Let's look at DCR to DCA. So constant density. DCR over minus DCA. Look at minus, right? Doesn't matter, we can make it, yeah. So let's see what we get. So that's DCR dt over minus DCA dt. Well, I'm sorry. RR over minus R. That's more precise. So what is RR here, other than the railroad? Rate of production of R. K1. Uh-huh. Good. Over minus RA. What is minus RA? Good. So we can cancel the CBs. So immediately, what we see here is the product distribution doesn't depend on CB. Or at least the instantaneous fractional yield doesn't. So this is equal to 1 minus K2 over K1 CR over CA. And this is DCR over minus DCA. So DCR to DCA, so I have the minus sign. So I flip this, so I put a plus here, a minus, a plus. And then I subtract that K2 over K1, CR over CA is equal to minus 1. And this is a first order linear differential equation. How do I solve all first order linear differential equations? With an integrating factor. So the integrating factor, here I've got this thing. So the integrating factor is e to the minus, e to the integral, K2 over K1, CA dCA, with the minus sign. So the integrating factor, in this case, is e to the minus, and I've got a K2 over K1 times the log of CA, which gives me e to the CA to the minus K2 over K1. I'm sorry, e to the log, which is just CA to the minus K2 over K1. So I multiply both sides of the equation by that. I have e to the minus K2, I'm sorry, CA to the minus K2 over K1, DCR DCA, minus K2 over K1, CR over CA, is equal to CA to the minus K2 over K1. And the claim is that the left-hand side is just equal to DDCA of e to the minus K2 over K1, CA to the minus K2 over K1, CR. And let's just convince ourselves of that. So if I take DCA of CR, did I lose something? Well, let's see. So if I take DDCA of CR, I get the first term, because this just comes out. And when I take DDCA of CR times DDCA of the next term, DDCA of the next term, you have to remember what DDX of x to the n is. That's equal to nx to the n minus 1. So this just gives me a minus K2 over K1, CA to this thing minus 1. That's CA to this thing over CA. And that's exactly what I have here. Okay? And that's equal to CA to the minus K2 over K1. And now I can try to solve this. I multiply by DCA and I integrate. So the left-hand side gives me CA to the minus K2 over K1 CR. Actually, let's multiply by CA, DCA, and this goes from 0, CA, 0 to the minus K2 over K1 CR of 0 to CA to the minus K2 over K1 CR of tau. And this is CA of 0, CR, CA, tau. Minus CA of 0 to the minus K2 over K1. CR of 0 is equal to the integral of this thing. So again, this is equal to CA to the minus K2 over K1 plus 1 over 1 minus K2 over K1. Evaluated at tau minus evaluated at and since we're at the end of the hour, I will manipulate this into a better form next time. What I'd like someone to do is to write down this equation, and at the beginning of the hour, if you get here before me, rewrite this equation on the left side of the blackboard. Can someone take responsibility for doing that? Hello? Rewrite this equation on the board so I have it there when we start next time.
This classroom, you said, Professor?
I'm sorry?
This classroom?
Oh, I have to get a room. I have to make sure I have a room.